Hello, I'm David from Elastic, and I'm super happy to participate in the Open Conference 2024 pre-event. And today I will be talking about how you can search actually for similar musics using a vector database, which is Elasticsearch. And I'm working at Elastic for more than 10 years now. So Elasticsearch, you might know, it's for search, and Elasticsearch is based on the fantastic Apache Lucene library, which is a Java library where you send document, you index document, and anytime you want to index a document, there is something which is happening behind the scene. So to take an example, I'm going to take this sentence as an example, which is, these are not the drawings you are looking for. When you want to index this content into Elasticsearch nowadays, what is happening behind the scene? We are going through an analysis process. And the analysis process basically is going to remove, for example, here, the HTML characters that we don't need anymore. It's going also to tokenize the content, which means split at the space, basically. So we will produce some tokens, and for every single tokens that we produce, then we will go through a filter, like the lowercase filter to lowercase everything, the stop filter, which is going to remove the standard words of a given language, English, for example, and snowball to take the infinitive form of the verbs or the radicals form of the words, for example. So when you want to index such a sentence, what is happening behind the scene, these are not the drawings you are looking for, is actually indexed as droid you look. And when you search, the same exact process is happening to the text you are searching. So that's how search is working nowadays. The problem with that is that we are losing the meaning of the sentence. Here, I index droid you look, but those were not the droids we were looking for, right? So this is a total different meaning here. And if I'm searching for machine, it won't work because I did not index machine actually, but only droid. So of course, with Elasticsearch and Lucene, you can use synonyms behind the scene. But anyway, this is something we want to solve. And if we want to solve those problems, what we want to build at the end is a semantic search. And semantic search is totally different than literal matches or token matches, if you wish. To implement a semantic search, what you need to do is to actually use a vector database. And you may not know that Elasticsearch is actually a vector database, and you can use Elasticsearch for vector search. So I'm going to start to explain what is a vector, because this is an important thing to know. A vector is basically helping you to represent your data. Here I have one axis where I want to represent my image, if it's realistic on the left, or if it's a cartoon on the right. And so I put Princess Leia on the left because she's realistic, and Darth Vader here on the right is not realistic, he's a cartoon. Of course, I want to represent multiple data aspects, like if it's a human or a machine. So for Leia, for example, she's human, so the coordinates are -1 + 1. But for Darth Vader, it's cut in the middle, so I would say it's half human, half machine. So he's a cartoon, so the coordinates for him are +1, 0. The goal of that is to put all the data in this space, in this embedding space, how we call it. So for example, let's add Luke Skywalker. So he's losing his hand, so that's the reason he has 0.8 as a human. He's not totally human. And then we have Obi-Wan Kenobi as a cartoon, for example. So those are the coordinates for Obi-Wan Kenobi. And same thing for a machine. So this is what we have. We have that, but not only with 2 dimensions. You can think about many, many more dimensions, like thousands of dimensions, for example. What we want to be with that? We want to be able to search. And the goal is, for example, if I'm searching for this image, I want to find what is the closest image from this one. Obviously, we can mentally represent where we will put Han Solo here on the picture, and probably the closest person or the closest data that we have on our data set here would be Leia at first. And then Luke, and then, hard to know, maybe Obi-Wan, maybe the machine. Let's say this is Obi-Wan, for example, and then the machine. What we are sure is that Darth Vader is at the opposite of what we are searching for, which is Han Solo here. So, how do you index vectors inside Elasticsearch? So, to do that, you need to take your data set as an input, transform that into dense vectors. So, dense vectors are the vector representation of your data. To do that, you will use a machine learning model that you need to find. There are a lot of machine learning models available on Hugging Face, for example. Elastic's also providing some machine learning model if you wish. But that's the goal of the machine learning model, is to transform something into a vector. During the demo I will show you in a moment, you will see that I'm going to transform audio content to a vector representation of the audio content. To implement that into Elasticsearch, so you create an index, and you are going to add, in addition, for example, of the description field that you can have in your dataset, which is a text field. Basically, you want to run a full text search on it. You are going to add a new field named desk embedding, which is a dense vector type. And this dense desk embedding field will contain the vectors that you computed before. So when you are sending a document to Elasticsearch, you are posting the document, so a JSON document, which represents your data, into Elasticsearch. Here, I'm sending a text within the description field that we saw before. And what is going to happen behind the scene? It's exactly the analysis process that I mentioned at the beginning of this session, where we split at tokens and do lowercase and all those things. But here we want to do more. So we want to actually send our description, our text, into a script, let's say a Python script. It could be a JavaScript if you are using Longchain4j, for example. And it's going to generate a vector, and we are going to add this vector, this generated vector, into our JSON document and send that to Elasticsearch at the end. You can do that for images as well if you want, whatever the data you have. How do you search then? So that's the second part. You have a query sent by a user, and you are going to transform the query made by the user using the same machine learning model that you use at index time. You are going to use the same at search time, and you are going to build a vector representation of what you are searching for. How it works? It works with a KNN query inside Elasticsearch. So you have this text, summer clothes. You compute using the same process as we saw before, a vector, and then you run a KNN search, which you can see in yellow, on the desk embedding field, which contains the dense vector, and you pass the vector that you want to search for. Because we are in Elasticsearch, you are also benefiting from all the power that you know with Elasticsearch already, like filtering, for example. It's not useful to present all the results, for example, if you are looking only on a department for women in your e-commerce website, for example. You can have pagination, you can have aggregation to compute statistics on top of the result set that you want. So all that is built in, actually. So then you have your vector representation, and the goal of that is to compare the vector representation of the query to all the vectors that you have indexed previously and find what are the nearest neighbors that you can find, and then show the result to the users. Remember what we did previously? We used, for example, we indexed Princess Leia and Luke Skywalker, and we wanted to search for for Han Solo, for example. How we do that? We need to compute a similarity of the vectors. So basically, the closest the angle between the query and the document you are searching for, the closest it is to 0, then the better. It means that the vectors are similar. How you compute that in a computer? You use the cosinus actually of the angle. And you compute a score which is 1 plus the cosinus divided by 2. How it works? So if you have similar vectors, the angle is close to 0 and the cosinus is close to 1, which means that the score is close to 1 because 1 plus 1 divided by 2 equal 1. If you have orthogonal vectors, then the angle is close to 90 degrees. Cosinus of this angle is close to 0. So we have this score, 1 plus 0 divided by 2 equals 0.5. And then for opposite vectors, the angle is close to 180. And so the cosinus is close to minus 1. 1 minus 1 divided by 2 equals 0. And so we have a score going from 0 to 1. 1 is actually the vectors are the same, basically. So this is my podcast. I'm actually a DJ and I love DJing. I hope you are still listening to me. Yeah. And the goal of this is to show you a demo using search and music, actually. So we want to search for music. So here I have some records, but this is not what I'm going to show you. So what I have some audio files on my laptop, and I'm going to use a machine learning model, which is going to transform my audio file into a vector representation of each audio file, and then it will index that into Elasticsearch. And then I will be humming a song, and I'm going to go through the same exact process as we saw previously. I will generate an embedding out of this audio content, and it will search using the kind search that we saw before, and this will going to present that to the end user. So let's do that. Here, I have a Python notebook here. So I already started a few things. So I installed dependencies. I think I did that already. So let's do that again in case it's not loaded. So I'm installing some dependencies. I'm importing some libraries. And the important part of all that is this one here, the model, is where all the smart part is happening. So this is where we are going to transform the audio content to a vector representation. We are going to do the inference here. So first thing I want to do is to test the connection with Elasticsearch. I'm running on Elastic Cloud here. I have the latest version of Elasticsearch, so all good. So what I'm going to do here, I'm going to first create a new index, and this is the mapping configuration of my index. So here in this audio embedding field, I'm saying that it's a dense vector. I'm using the cosine similarity by default, and out of my machine learning model, I will get back 2048 dimensions from my model. So I created this index. I have some script to list an audio file from a directory, which is not super important here. But here, more important, I have this method which is responsible to get the embedding, so the vector representation, from an audio file. So I'm loading the audio file, and then I'm calling my machine learning model, and I'm running the inference here. And out of that, here I will have a list of vectors, one vector with a list of floating points, which represent my vector here. So there is also a method to index into Elasticsearch. This is totally classic in Elasticsearch. So you basically index a JSON document here. And then I have this search method where I'm searching using the KNN method that I mentioned before, and I'm passing the vector here as a list of floats. So let's run that. Here are the list of files that I have on my laptop, so not that much. And what I'm doing for each file, I'm getting the embedding of the audio file, so generating the vector representation. And then I'm storing that into Elasticsearch, so the vector. And this is what you can see here, by the way. This is the representation, the vector representation of each audio content that I send to Elasticsearch here. And then when I want to search for a similar song, I'm going to first load my file that I want to search for. So listen to that. Na 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 na. So it's me singing, basically. So the thing I need to do is to generate the embeddings as we saw previously, the same thing that we did at index time, but now at search time. So here I have my list of vectors, and I can run the search and query my dataset with this vector representation of me humming a song. So let me show you the first hits, so the first 5 ones. Obviously, the first one is myself, because I'm sending the same content at index time and at search time. It should be 100%, but actually it's close to this one. But anyway, we don't want to use this one because this is the same. So let's focus on the second one here. If I'm looking at the second results that I have in my result set, so it's super similar, right? But there is a trick here, and you need to understand that. Actually, you need to understand what the machine learning model you are using is doing behind the scene. And if I look at the GitHub repository of the machine learning model that I'm using, I have seen that, actually. So what kind of classification is doing this machine learning model? Is trying to classify if the sound has a speech, male speech, child speech, if it's a baby, laughter, if someone is singing, if someone is humming a song, maybe it's that, some other songs that I don't want to comment here. And then at some point, so here some animals, but then at some point, is that music? Is that musical instrument, guitar, electric guitar, acoustic guitar, etc., organ, drums, percussions, and all that thing. So this is all the classification which is happening behind the scene, and also the type of music that you have, like if it's opera, classical music, and etc. And also a cappella. And probably what I'm doing here is a cappella. So that explains why this second hit was the closest to me, because both of them are a cappella. It's not about the music itself and the notes behind the scene, it's more about the classification of the content. So if I'm looking at the next one, so it's still a cappella with some music behind, which explains that it's close, not that close as the previous one, but still close to the result set. And the next one. So it's still a cappella with some drums behind, so maybe that explains the score that we saw as well. And the last one. So here we have an opera singer. Obviously, I'm not an opera singer, but the opera singer is probably doing some, or is seen as a cappella singer. So that explains why it's on the 5th position on my result set here. So this is what I had for you today. You can check this QR code if you want to replay the demo that I played today. And thank you for your attention and have a great conference.